Um, okay, so fall 2018 final. Okay, the first question is about classification. So um, we took a big sample of people um, who voted and didn't vote, and we tracked how many social media posts they made that were political and non-political. So non-politicals on the x-axis and politicals on the y-axis. And then this triangle here is a subject in our test set that we want to explore. Okay, so A is if we use three nearest neighbors, how does it classify? Um, so the three nearest neighbors are this one, and then this one. So that's two non-voters and one voter.
Hmm.
Wait, I did that right, right? Yeah.
I think
Okay.
the red dot next to the other red dot above the triangle is the same distance
Oh,
as
okay.
that blue X, but like
But
it's
regardless,
still,
it's non-voter, right?
yeah.
Awesome. Okay, non-voter. Okay. B is that we divide the data into test and training sets and find a 94% accuracy. So we think that's pretty good. So we decide to apply it to a test set from another country with less internet. Should we expect the accuracy to be the same, lower, or higher? Um, so the answer is lower,
Hmm.
um, and it's because our training sets, you can see it here, but if we
Hmm.
go to a country with less internet, way more people are going to be down here, and we have nothing in our training set that predicts points that are down here with very few social media posts. So the closest neighbors are going to have a really big distance from the points in this country, so it's going to be less accurate.
Could another reason, mm, could another reason be because the classifier is only applicable to the data that trained it, and the data that we used to train it was from the United States, not another country?
I think that's one possible explanation, but um,
What you just said is
that
the better one.
but I number one, this is a better one, and number two, if you went to another country, you know that it wouldn't be a perfect classifier, but it is possible that the accuracy could be the same or increased just by chance.
Hmm.
But here's an explicit reason why the accuracy would specifically decrease.
Okay.
Okay, so part C is now we're going to use a D distance classifier. So instead of taking the three nearest neighbors, we're going to take every point within 5 units of this. Um, so let's draw a circle with a radius of 5 that's centered at our triangle here. So 8, we're going to go here. So we're going to go up, and then it's going to go here, and then so this is 17 political posts, so if we go down by 5, it's 12. So we're going to go down here and then here. Okay, so everything inside this circle here is in our D distance. So you can pretty clearly see there's a lot more voters here.
Hmm.
So we're going to conclude voter. Okay, that's question one. Let's go to question two. So we have a table with two columns. There's tenancy, which is how long you've lived there in days, and then rent is how much rent you pay. And these are all two-bedroom apartments in one city. Okay. I wish my rent was 2,800. Alrighty. So part A, if we just
They
have
say
these
that it'll be like 1,000.
okay, if we just have these two histograms here, so rent and then tenancy, which are which are legit conclusions? Okay, so the first one is that the median rent is somewhere between 2,500 and 3,500. So we're gonna go in here and then right here. So this one is true because um, you can tell that the 50th percentile or the median of the data is going to be somewhere in here because everything on the two ends is less than 50% of it.
Yep.
And then, okay, for the second one is that there's a negative correlation between tenancy and rent. This one is not true. So it might appear to be true because the peak amount of tenancy is really low, but the peak amount of rent is higher. However, you could assign a pairing such that each low rent value is paired with a low tenancy value, and then each high rent value is paired with a higher tenancy value. So by looking at these two histograms alone, it's impossible to know whether or not there's a positive or negative correlation. Okay. The third one is that the mean tenancy is higher than the median tenancy. So we're looking at this histogram here, and this one is true. Because the median is where you can find the peak of the data, so it's going to be somewhere towards the left of the histogram. But there are values that are much higher, like outlier values, that affect the mean far more than they affect the median. One good example I like to use when figuring out whether the mean or median is higher is when there's a lower bound to how low values can be, then the mean is generally higher because the lowest you can go is 0, but there's no maximum. Another example that works like this is people's incomes, right? There's a lot of people in the lower to middle incomes, but just a few people who make a ton of money can increase the mean by a lot without changing the median by that much. Okay, and then the fourth option is that the mean is lower than the median. It's not, we just showed that the mean is higher.
Yep.
Okay, so we have a notebook and we find the following things. We find that the correlation between rent and tenancy squared is 0.214. And then we have the standard deviation of rent and tenancy. Okay.
Why would you square the correlation? I was looking at that and I was wondering that.
This is, so if you take R squared in statistics is a value called the determination coefficient, I want to say. I'm not exactly sure, but we don't use it in this class. The reason we squared it here is to troll you, and we'll see why in the next question.
That's so mean.
Yeah. Okay. Okay, so B is find the probability that the correlation between tenancy and rent is 0. So the answer to this one is just 0. And that's because we literally know that the square root, or the R squared is 0.214, meaning the R is the square root of 0.214, which is not 0. So it's clearly not 0. And yeah, the probability that the correlation is 0 is nothing. Okay, C is the slope of the regression line for predicting the tenancy from the rent. And this one is impossible to determine.
That's an annoying sound.
I know.
It's because I have Facebook open. I closed it. Okay.
So the reason it's impossible to determine is because the formula for slope is R times SD of Y over SD of X. We know SD of Y and SD of X, but we don't know R. We know R squared, but so if we take the square root of this, it could be positive or negative.
Oh.
And for that reason, we can't say we can't just say like square root of 0.214 times SD of Y over SD of X.
Got it. That was sneaky.
Yeah.
Okay.
Okay. Now part D is the RMSE of a regression line predicting rent from tenancy. So the formula for the root mean square error of a regression line is the square root of 1 minus r squared times SD of y. So we know r squared, it's 0.214. So we can say square root of 1 minus 0.214 times, and then you want the value, you want the SD of the variable that's on the y-axis. And the way we know which one that is that the thing you are predicting should be on the y-axis. So in this question, we are predicting rent from tenancy. So rent is the thing we're predicting. So we take the SD of the rent, and that is 549.5. So that would be our answer there. All right, E. We want to predict the rent for an apartment where the longest tenant has lived there for 3 years. So one night you write code to bootstrap a 95% confidence interval, and then you made some mistakes. So we want to correct this whole thing. Okay, so predictions equals make array. That seems fine to me. For I in np.arrange 5000, that seems good to me. Samp equals housing.sample with replacement is true. That looks good to me. You're bootstrapping a new sample. M equals slope of housing, tenancy, and rent. Okay, so here, we don't want to use housing here. We want to call it on SAMP.
Okay.
Because we don't want to use the original sample. Otherwise, we get the same value every time. We want to use the bootstrap. Same with the intercept value. We want to put SAMP here.
And on the slope line, shouldn't it be rent and then tenancy? Like doesn't it switch up the variables?
Let's see. So it's saying that it says we want to predict the rent, meaning the rent should be the y-axis. So tenancy comma rent is the correct way.
Okay.
Okay, then np.append of predictions, comma, m times 1095 plus b. So this is not correct because you're not setting this appended array to anything. We need to do predictions equals np.append. Okay. Then left equals percentile 5 predictions, and the right is percentile 95. So this actually is not a 95% confidence interval. This is only a 90% interval. So to fix that, we need to change these values to 2.5 and then 97.5. Okay. Question 3, bandages. Okay, so we have this table which has 2 columns. It's the size of your bandage and then how much they charge for it. So this is a histogram of all the small bandages and their prices. So question A is, what percent of small hospitals have bandages that cost at least $1 but less than 2? So $1, let's change the color. $1 is right here, and then $2 is right here. So we want to find the area in these two bars. So area of a histogram is width times height. So the first bar, the width is 0.5 because it goes from 1% or $1 to $1.50. So 0.5 times how high is it? It's 20%. And then the second bar is also 0.5 wide. And then how high is it? It's 30% high. So 30%, and that's equal to 25%. So there's our answer there, 25%. Okay. Part B, fill in the blanks so that the array large medians contains 5,000 bootstrap samples of the median price for large hospitals. Okay. On these questions, I always like to do the easiest parts first. And for me, the easiest part is the for loop. So it wants us to do it 5,000 times. So for I in np.arrange 5,000. Okay. So now T equals bandages.where. And so what where does is that it takes certain rows out of an array or out of a table. So we want to filter the table so that it only has large hospitals. So that's what we're going to do. So we're going to do size equals large. Another way to do this would be r dot equal to large, but they both work. Okay. So large medians is probably going to be an array that we store stuff in. So we want to create it. So we're just going to do make array. Whenever we have a for loop that does a simulation, we need to create an array somewhere. So we're going to do that there. So now it gives us 3 open-ended lines. But there are 3 things to do so we can fit them in. So the first thing we want to do is take a bootstrap sample. So the way we write that is we call this, let's just call this bootstrap equals, and then we're going to sample T, and then we want with replacement to be true. Because otherwise we'd just be shuffling, and that's not what we want.
Right.
Okay. The second thing we want to do is we want to calculate a median. So we're going to say median equals, and there's 2 functions we can use. We can use np.median, or we can do the 50th percentile, but here we'll do np.median. And then we need np.median takes in an array. Mm-hmm. So we can call an array out of a table by using the column function. So we're going to do bootstrap.column of price. So now we have our median, and the last thing we want to do is add it to an array. So large medians equals np.append large medians median. And then we're done. Okay, part C. Fill in the code so that the array CI98 contains the endpoints of a 98% confidence interval. Okay, so the way we find the endpoints is that we do 100 minus 98, and then we do all over 2, and that's 1%. So our endpoints are going to be at the first percentile and the 100 minus first percentile, which is the 99th. So left is going to be percentile, and then we want the lower end, so we'll do the first percentile of large medians. And then the right endpoint, we're going to do percentile 99 large medians. Okay. Question 4. Did you get this far when you did this one?
Yeah.
Okay. So we have 2 ice cream shops, and they sell mystery pints, and they tell you the probability that you get each one. So, part A, you buy 5 pints from Game of Cones. What's the probability they're all vanilla? So these, you're drawing pints from here, and then these are all drawn independently. So we can say that the probability of getting it 5 times is the probability of getting a vanilla once, and then to the 5th power by getting it 5 times. So this is going to be 0.3 to the 5th power. Okay. Part B is that you buy 5 pints from Game of Cones. What's the probability that they are all the same flavor? So there's 3 ways to get all the same flavor. You can get 5 vanillas, 5 maples, or 5 raspberries. And what you notice is that getting 5 vanillas and getting 5 maples are they're mutually exclusive, meaning that like the probability of both of them happening is none. Because if all your pints are vanilla, there's no way they can be maple or strawberry. So in the case that we have 2 events that don't intersect at all, the probability of one of them happening is the probability of the first one happening plus the probability of the second one happening. And in this case, we have 3 scenarios, so we can add in the probability of the third scenario happening too. So the chance that we get 3 or 5 vanillas is 0.3 to the 5th, which we just calculated. And then the probability of getting 5 maples is 0.15 to the 5th. And then the probability of getting 5 raspberries is 0.55 to the 5th. Okay. Part C. Your roommate randomly picks one shop where each shop is equally likely to be chosen and buys you a pint. What is the probability that it is raspberry flavored? Okay, so we can kind of draw our own tree diagram here. So let's do that. Zoom in. Okay, so since both stores are equally likely, we have a 0.5 chance of going to the first store and a 0.5 chance of going to the second store. And then we have our 2 stores. And then we have 2 possibilities, which are raspberry and non-raspberry. So we're going to do R for raspberry and then NR for not raspberry.
I like these store names. They're funny.
I know. Okay, so at Game of Cones, the probability of raspberry is 0.55, and then the probability of not raspberry is 0.45. And then at Sunday Night Live, the probability of raspberry is 0.05, and then non-raspberry is 0.95. So the probability that it's raspberry flavored equals probability of raspberry given you're at Game of Cones plus the probability of raspberry given you're at Sunday Night Live. So therefore, probability of raspberry equals, so the probability of getting a raspberry at Game of Cones is the probability of going to Game of Cones in the first place times the
Hi,
probability of raspberry.
Hey, Garish.
What's up?
Then,
Are you in the middle of conversing with the people?
Yes.
I wondered what you wanted for dinner.
Can you text me?
Thinking about pasta. Egg
Pasta.
sauce.
Okay. That sounds fine. Sorry.
no, don't worry about it. Okay. Then the probability of raspberry given here at Sunday Night Live is 0.5 times 0.05. 0.05. And then that's your answer here. Okay. So part D is that you randomly pick a shop where each is equally likely, and then we buy a pint. If it's vanilla flavored, what's the probability it came from Game of Cones? So we can draw another tree diagram. So it's going to be, again, it's 0.5 for each store. And then in this case, we're going to do vanilla and not vanilla. And so at Game of Cones, the probability of vanilla is 0.3. So not vanilla is 0.7. And then at Sunday Night Live, the vanilla is 0.7. And then not vanilla is 0.3. So we want the probability of vanilla. Wait. Oh, wait, no. We want the probability that it's Game of Cones given that we have a vanilla. So the way we can do that is calculate the probability of Game of Cones given vanilla, so 0.5 times 0.3, and then divided by all the possibilities for which you can get vanilla. So that's going to be what we have up top, so 0.5 times 0.3, plus the probability of going to Sunday Night Live and getting vanilla, which is 0.5 times 0.7. So that's our answer for this question. Okay. So now an ice cream researcher decides for an entire semester, they'll buy 1 pint every weekday. So because of their schedule, they go to Game of Cones 3 times a week and Sunday Night Live 2 times a week. Okay, so the researcher asked their roommates for help eating the ice cream on a weekday, but they hate anything maple flavored. So what's the probability that today's pint is not maple flavored? Okay, so we can draw a tree diagram again, and we're going to do Game of Cones and Sunday Night Live. But now the probabilities are switched up. So if they go to Game of Cones 3 times a week out of 5, that's a 0.6 probability of going there. And then for Sunday Night Live, it's 0.4. And then we want maple versus not maple. So M, NM, and then M and NM. Okay. So now the probability of maple here is 0.15, and then not maple is 0.85. And then for Sunday Night Live, maple's 0.25, and then not maple's 0.75. Okay. So now with this tree diagram in mind, we have probability of not maple equals so the probability of not maple at Game of Cones is 0.6 times 0.85, and then we're going to add on the probability of going to Sunday Night Live and getting a not maple, so 0.4 times 0.75.
Alternatively, could you have gone 1 minus and then like switched out like the 0.5 for the 0.15 and the 0.5 for the 0.25?
Yeah, we could have done 1 minus 0.15 and then 1 minus 0.25. Yeah, that also works.
Okay.
Oops, what did I do? Okay. Now we're on part F. So, suppose the researcher suspects that the mystery pints do not follow the distribution that the shop claims. They keep track of the flavors when visiting Game of Cones and then conduct a hypothesis test. So their null is that the mystery pints are distributed according to the probability distribution, and the alternative is that they're not. We're going to use a p-value cutoff of 0.01, and so the best test statistic is the total variation distance between expected and actual distributions. And the reason why is because the flavor of ice cream is a categorical variable, and we have multiple categories. So the best way to do it is using TVD. Okay, part G is if the null is true, what is the probability that their test will fail to reject the null hypothesis? So failing to reject basically means accepting it. So basically, if the null hypothesis is true, what's the chance that we're going to be correct? And here we're going to use a formula for error probability that we learned before. So it's the probability of falsely rejecting the null equals the p-value cutoff. So our p-value cutoff is 0.01. So that's the probability that we mess up. So the probability that we don't mess up is 1 minus 0.01. So 1 minus 0.01 equals 0.99. So that's how we get that. Okay. Part H, the researcher conducts the hypothesis test above and obtains a p-value of 0.12. Which of the following are true? Okay. The first two are instantly false, because once we do a test, we either confirm or reject the null hypothesis. There's no probability associated with it. We either say we're good or we're not good. There's no in between. Okay. Then the third option is that 12% of simulated values are greater than or equal to the observed value. So remember that larger values of a test statistic should favor the alternative. And so in this case, this is correct, because if 12% of values are greater than the observed, then that means our p-value should be 0.12. Okay. The fourth option is that we should reject. We should not, because the p-value is greater than the cutoff. And then the last one is that we should fail to reject, and this one is true. Okay. Question 5 is library books. Did you get to this one?
I did. I have a question about the last one, part H.
H? Okay, we can get there. There's no
Um,
part H. Oh, wait. Are you talking about part H of this question?
yeah.
Okay.
I was just wondering because I get why the third one like makes sense, but when I read it, I would thought they were like tricking us because it says greater than or equal to. It doesn't specify in which direction. Like it doesn't say like that the Game of Cones distribution was like greater than or equal to. It just says like it was not equal to, so it like theoretically could be on like either side.
Uh-huh.
So I was just wondering about that one.
Okay, so when we do total variation distance, we're
Mhm.
taking the absolute differences between the observed and the expected proportions of ice cream flavors. So
Okay.
that controls for the fact that it could be greater than or less than.
Okay. So good. Okay. Okay. I got to part of this one. I got through part A, and then I stopped because B was confusing.
Okay, that's fine. So we have two tables. One has a bunch of books and the number of times they were borrowed. One has every author, their year of birth, and the books they wrote. Okay. So part A is the average number of books borrowed over all books published in the 90s. So A equals books dot blank of blank comma blank. So the first thing that pops out to me is that we want only the books from the 90s. And that means that we should take certain rows. So we're going to use the where function. And then we want to filter by the year published. So the column is called year published. And then the predicate function we want to use is r.between. And then we want to do 1990 and 2000. Because r.between, it does not include the last number in it. So it will stop at 1999 properly. If we did r between or equal to, then we could have done 1990 to 1999, but we didn't, so. Okay, now blank of a dot blank blank. Okay, so what are we trying to compute? We're trying to compute an average. So we want to put np.average here of a dot blank of blank. And so np.average takes in an array as an argument. So we want to take an array out of this table. And the best way to do that is by taking the column. So we're going to do column of, we're taking the average of times borrowed. So we're going to say times borrowed. Okay. B is the most popular author at this library. So to figure out the popularity of an author, we need to know the author's name, and we need to know how many times their books have been borrowed. So x equals blank dot select of blank blank. So this is telling us that we need to make a table with only two columns. So the first argument is going to be books. And then the two columns we select are, as I said, we want the author and the number of times their books have been borrowed. So we're going to do author and then times borrowed. Okay, then y equals x dot blank of blank comma blank. So if we want to take each author and add up all the times that their books have been borrowed, the function that we want to use for that is group. So we're going to do group. And what are we grouping by? We're grouping by the author. And then what do we want to do with that? We want to add up all the times their books have been borrowed. So we're going to add in another function, which is going to be np.sum.
Okay.
So then z equals y dot blank of blank comma blank. So now we want the most popular author at the library. So we should probably figure out which author has the highest sum of times borrowed. And the way we can do that is by sorting the table. So we're going to do z equals y dot sort. And what are we going to sort based on? We're going to sort based on times borrowed. But since we grouped based on the sum, the column name is going to be times borrowed sum. Then the second argument that sort takes in is descending equals false or descending equals true. So the way we figure out which one we should use here is the next line it calls item of 0 on a column, meaning it's taking the first thing. Therefore, we want the highest, the most popular author to be at the top of the table. So we want to sort by descending equals true, so that the highest values are at the top. Okay, then we want the most common or most popular author, so we're going to do z.column of author. And then we take item 0, and then we get the most popular one. Okay. Part C. This one is kind of trippy because you don't need all the lines, which makes it hard to figure out exactly what they want. But we'll, so this wants a new table with 1 row per book, and then it wants the title, and then the author's age when it was published. So the new column should be called author age. So we have 2 tables, and we want to combine some information in them, because if we want to find the author's age, we need to subtract the year published and the year born. But the thing is, we don't have both of them in the same table. They're in 2 different tables. And the way we get them to get together is the join function. So we'll call this join equals, and we want to do books.join, and then we're going to join based on the common column that they have, and that's going to be author. And then the second argument that join takes in is the other function or the other table that you're joining it with, and that's going to be authors. And then the third argument is the name of that column in the other table. So in the books table, the author column is called author, and then for authors, the author column is called name. So we need to pass in the name column. Okay. So now we need to put in the author's name, or sorry, the author's age at the time of writing. So we're going to do joined equals joined.with column. And then the question wants us to call this author age. So new column called author age. And then the way we get the author's age is that we take year published, and then we do year published minus year born. And so we have joined.column of year published, and then we can do minus join.column of year born. Okay. And then now we're actually done, because we have the author's age and we have the title, and then this piece of code down here does blank.select of title and author age, meaning it's just taking those 2 columns, so we pass in joined into there.
Got it.
Okay. Part D is select all the 3 that are true, given that the average borrowed is 80, and then the standard deviation is 20. Okay. First one is that at least 75% of the books have been borrowed 40 to 120 times. This is true. Because of Chebyshev's inequality, it says that 1 minus z squared of the, 1 minus 1 over z squared of data is within z SDs of the mean. So if we plug in 2, because 40 and 120 are 2 SDs away from the mean, if we plug in 2 here, it'll say 1 minus 1/4, or 3/4, or 75% of the data is within 2 SDs of the mean. And this also should say at least. And remember, this is no matter what the distribution looks like. Okay. Now The second and third ones are both false. And this is because these are both reliant on the distribution of times borrowed being approximately normal. We don't know if it's approximately normal or not. And the central limit theorem does not apply because we're not taking the sum or average of anything. So, no, these are not true. Okay. Part E is you're testing whether there's a difference in the number of times paperback books are borrowed. Provide a null and alternative. So the null is that paperback and hardcover books are borrowed at the same rate. And then the alternative is that, remember that the question is saying there's a difference. It doesn't specify which direction. So then our alternative would just be that paperback and hardcover are not borrowed at the same rate. Okay. All right, part F. Naomi doesn't have the full data we do, but she wants to estimate the percentage of books that are paperback, and she's going to sample 250 books and then gets a confidence interval of a certain amount. So fill in the ovals next to all correct statements. The first one is that if she convinces 1,000 patrons to go through the same process, then 95% of them will produce intervals containing the true percentage of paperback books. This is true because remember that we can't say anything about whether an individual confidence interval contains the mean or not. We can say that if we do a bunch of repeated random samples and take a bunch of confidence intervals, then the percentage of them that will contain the true mean is expected to be the confidence level, so 95%. Okay, the second one is that if we sample 4 times as many books and repeat, the new confidence interval will be half as big. This is true because the formula for SD of sample means equals population SD divided by the square root of sample size, which we can call n. And then if we do the calculation here, what we can find is that if we replace n with 4n, because we're multiplying the sample size by 4, then it would be population SD divided by square root of 4n, which is equal to population SD divided by 2 square root n, which is equal to 1/2 times population SD over square root n. So that's how we know that the new confidence interval will be half as big, because if we have 1/2 that comes out. Okay. The last one is that if we repeated the same procedure with 1/4 as many books, the interval would be about half as big. So that's not true, because instead of using 4 times as many books, we're only using 1/4 as many. So no, it's not true. In fact, it would actually be twice as big if we did that. Okay, part G. We decide to save time by sampling 1,000 books from a single row and then using the same process to get a confidence interval. Is this a good idea? Yes or no? So the first is that this is not a good idea because you need to use the bootstrap to obtain the confidence interval. That's not true, because you can bootstrap with 1,000 books the same way you bootstrap with 250. The second one is that this is not a good idea because it is not a uniform sample. That's correct, because what if you're in like the paperback section of the library? Of course, every book you grab is going to be a paperback. So it's not a completely random sample. It is not a good one to use. Okay. The third one is that it's not good because it's possible that books on the shelf might not be representative of the rest of the library. This one is also true for the exact same reason. The fourth one is that this is not a good idea, and instead, we should use a 99% confidence interval to make up for the fact that all books came from the same shelf. The 99% cutoff is completely arbitrary, so no, we don't want to do this. And then the last two say this is a good idea, but it's not, so these are false. Okay, question 6. We have two tables called Season 18 and Season 16, which has the Cal score and the opponent score in the football games. And so we want to know if the spread, meaning the average margin of victory, was better in 2018 than 2016. Okay. So first we want to set up hypotheses. So the spread of the games in 2018 come from the same distribution as blank, and that's going to be the spreads in 2016. Okay. Alternative is that the blank come from a distribution with a larger blank than the blank. And so the question specifically says that we want to know if we did better in 2018 than 2016. So if we did better, then the spreads are going to be higher because we won by more points. So what we're going to say is the 2018 spreads came from a distribution with a larger average than the 2016 spread. Okay. Part B, our test statistic is going to be the difference between the average spread of games coached by Wilcox and the average spread coached by Dykes. So we want to get this table called combined. And it should have as many rows as the season 16 and 18 rows combined. Okay, so the first two rows are coach 18 equals season 18 with column blank Wilcox, and then with column blank Dykes. So what we're doing here is we want to add a new table or a new column to each of the season's tables with the name of the coach. And it doesn't matter what we call the columns as long as they are consistent. So we'll call both of them coach. So this one's going to be coach again. And then we're going to use this really useful hint right here, which is that table1.append table2, assuming that both tables have the same column labels, it can just toss the rows on top of each other. So combined is just going to be season 18.append season 16. Okay.
Would it not be coach 18 append coach 16?
Oh, that's a good point. You're right. Okay. Combined equals combined with column. And then we can see in the picture that the combined column has, or the combined table has a column called spread. So we're going to add spread to the table. So spread, comma, and then how do we calculate spread? We take the Cal score, and then we do Cal score minus opponent score. So we're going to do combined dot column of Cal minus combined dot column of opponent. Okay, and then combined equals combined dot drop, and then the combined table, we don't see Cal or opponent, so we're going to drop those two. Okay, part C. We use a simulation to conduct a hypothesis test. Which hypothesis do we base our simulations on? That's going to be the null. Always simulate under the null because you are assuming it's true until you're proven otherwise. Okay. Using the table combined, complete the code below so that the array diffs will contain 10,000 simulated values. You might not need all the blanks, but don't add extra lines. Okay, so first we need to make an array. So we'll do diffs equals make array. Then our for loop loops 10,000 times. So for I in np.arrange 10,000. Okay, so first we should know what kind of simulation we're doing. So this is an A/B test because we're trying to see, or our null is that the 2018 and 2016 spreads come from the same distribution. So the way we do an A/B test is that we shuffle the labels. So we'll call this shuffled equals. And so we want to take the labels, which is coach in this case, and just shuffle them around. So shuffled equals combined dot column of coach dot sample. And then since we're just shuffling, we're not bootstrapping, with replacement is going to be false. Then we want to make a new table where we replace the coach column from combined with our shuffled one. So we're going to do new table equals combined dot with column coach, meaning we're going to override the original coach column, and we're going to rewrite with shuffled. Okay, oops. And then the next line is going to be, so now we have a new shuffled table, and we want to get the average for each coach. So the way we do that is we're going to group by coach and take the average. So grouped equals new table dot group, and then we're going to group by coach, and then we're going to use the np.mean function. Oops. Okay. So now, let's see. So now the spread means are going to be means equals grouped dot column, and then the new column is going to be called spread mean because the original column was spread, and then we're using the np.mean function. So now means is an array with two elements. One is for one coach, and one is for the other coach. So the difference is, we can call it one stat equals means.item of one, meaning the second thing in it, minus means.column or item of 0. Notice that it doesn't matter what order we do this in because we are simulating under the null where we're assuming that the two elements should be the same. So it doesn't matter which one we use, first or second. Okay, so now we're going to append something. So diffs equals np.append, and it's going to be diffs, comma, one stat. One stat. Okay, so that's our simulation code. Okay. So now we want the correct line of code that computes the p-value. So let's see. So the first two, or the second two, are just not correct because this 0.05 here comes out of nowhere. In a p-value calculation, we're always comparing the observed to the diffs column. So the question is, do we do diffs array is or diffs greater than observed diff or diffs less than? So the p-value is finding all the values in our simulation that are more extreme than the observed. So more extreme means greater than. So we're going to use greater than or equal to. Okay. Part F. Suppose we get a p-value of really tiny. If our p-value cutoff is 0.05, can you conclude that changing coaches caused Cal to do better? No. And we have two reasons why. Or no, not two reasons, one reason why. And it's just that correlation is not equal to causation. There can be a boatload of other factors that made the team do better. For example, they got better players. They just got lucky. They played other teams that sucked. Who knows? But without a randomized controlled experiment, we cannot say that changing coaches is the reason we did better. Okay. Question 7 is mood and sleep. So we have the scatter plot. We have the R value, the SD of sleep, and the SD of mood. Okay. Part A is that if your friend wants to predict someone's mood from their sleeping habits, what slope would they obtain? So the formula for slope equals R times SD of Y divided by SD of X. And then, so the question is, what's Y and what's X? Remember that Y is the thing you're predicting, and then X is the thing you have. So we are predicting the person's mood, and we know their sleeping habits. So Y is going to be mood, and then X is going to be sleeping habits. So slope equals 0.71 times 15.86 divided by 1.72. So that's our slope. B. We use the bootstrap to get a 90% confidence interval for R, and which of the following statements are supported by the results? Okay. Because the students in the sample are chosen at random, the confidence interval does not contain 0, we can conclude increased sleep causes an improvement in mood. No, correlation does not mean causation. The second one, because the students were chosen at random and the interval does not contain R equals 0, we can reject the hypothesis that there is no association between the amount of sleep and mood with a cutoff of 0.1. This works because an X% confidence interval supports a p-value cutoff of 100% minus X. So in this case, 100% minus 90% is 0.1. So this is good. Okay, if we repeat the sampling process many times and computed a confidence interval many times, then 90% of them would produce narrower confidence intervals than this one. That's false. We would expect that 90% of them would create similar confidence intervals, or ones that contained the true R value. The last one is that the confidence interval is invalid because the bootstrap can only be used for the slope or predictions. That's not true. That's just something they made up. Okay, for the remainder of the question, assume that we had attained this data. So we try to fit a line using slope and intercept and get values of 6.8 and 12.24. So part C is draw a rough sketch of the residual plot. So we can draw that. And so it's going to look like this, where for low values of sleep, the residual is negative, but then it becomes positive, and then it becomes negative again. we want something that looks like this. And then it wants us to label the axes, so we can do that. The x-axis is hours of sleep. And then the y-axis is mood residual. And the x-axis label should stay the same. So it's going to be starting at 4. And then it goes to 6. And then 8. And then 10. And then the mood residual here is 0. And then at its peak, it's about plus 10 or so. So 10. And then the most negative residuals are about negative 20. So you can put negative 20 there. Okay, part D. Based on our graph, is linear regression a good idea? Basically, yes or no, and give a reason. So the answer is no. Linear regression is a bad idea, because if linear regression were good, then there would be no trend in the residuals. But our residuals look like this parabola here, indicating that there is a trend. So then part E, or wait, I should click the right answer. So the answer is no, linear regression is bad because there's a curved pattern in the residuals. Okay, part E is that your slope and intercept are trying to compute a predicted mood score for something. When you suggest a quadratic function instead of a line, your friend says the regression line gives you the smallest possible RMSE, so there's no way to get a prediction with lower error. Is your friend right or wrong? Select one and explain. Your friend is wrong. They are full of crap.
This tisk.
And the reason why is because the regression line minimizes RMSE for all linear models. It does not say anything about nonlinear models, including quadratic. So that's why a quadratic regression would probably be far better than a linear model. And
here's my graph of my time in data 8. So this is my sanity and happiness, and then we've got the midterm, project 2, and the final.
I like that.
Yeah.
Okay, I'm gonna stop the recording now.